They're fixing it? Okay. I'll be talking to you guys about multimodal parcellation. So using, here we go. Excellent. Multimodal parcellation of the human cerebral cortex. So three main topics. First, I want to give those of you who don't know about surface-based processing and sort of what we more generally call neuroimaging HCP style, a little primer on that, basically how to acquire, pre-process, and analyze your data to enable accurate parcellation. I was interested in a show of hands. Who in the room has done analysis on the cortical surface using cortical surface meshes before, as a show of hands? Well, that's actually very encouraging. That's quite a few people. And so for those of you who haven't done that, pay special attention to this first section here. Then we'll talk about the multimodal gradient-based semi-automated parcellation, HCP's multimodal cortical parcellation. And I'll close with a discussion of individual subjects, basically how we can use machine learning to automatically parcellate individual subjects even when they have atypical patterns. So what do I mean by HCP-style neuroimaging? So I mean collecting as much high-resolution imaging data on as many subjects as possible, using MRI acquisitions with adequate spatial resolution to image the structures that we're interested in. We want to be using our data pre-processing to remove distortion and motion without blurring the images. We want to represent data according to the geometric models that best fit, so things like surfaces for the cerebral cortex. We want to align cortical areas, not folds, across subjects. We want to use a data-driven, functionally and structurally sensible parcellation. And then finally, we need to do more than what has traditionally been done, the M&I coordinates in a table and paper. We actually need to be sharing the real results. So what kind of MRI data do we need for multimodal parcellation? Well, as we've seen in this course and will continue to see, parcellations have been defined based on architecture, function, connectivity, and topographic maps. So we can measure architecture with T1 and T2 weighted images as myelin maps or cortical thickness maps, and we can actually measure the other three properties with fMRI, among other things. And so the HCP acquired these data on just under 1,100 subjects at 3T, where we had all of these modalities. So cortical neuroanatomy sort of drives the initial question of what spatial resolution should we use to acquire our data. So over here on the left here, we have a group average map of cortical thickness, and then on the right we have a histogram of that map. And we can see that the mean cortical thickness is around 2.6 millimeters. Traditionally, people have acquired their functional MRI sort of in this region, say 4 millimeters or 3 millimeters. And so we're going to call high-resolution fMRI, fMRI that's less than the mean cortical thickness, which we can see here. I'll point out also that the minimum cortical thickness is 1.6 millimeters. So the HCP at 3T acquired data at 2 millimeters in less than a second, and at 7T we went all the way down to that minimum cortical thickness of 1.6 millimeters in 1 second. So for structural MRI for an HCP-style acquisition, T1 and T2 at 0.8 millimeter isotropic, and that's important because that gives us at least 2 voxels for even the thinnest cortex, the 1.6 millimeter cortex. The MP range and T2 space work well with this. Functional MRI, we want to be less than the 2.6 millimeter average thickness of cortex. Smaller is better if we have the SNR to do it. And also we want to image fast. So I'm not going to talk any more about this particular point here, but Tuesday morning we're going to have a symposium about the global signal where I'll give a lecture all about data cleanup in fMRI. And really fast imaging is critical for doing that well. We want to have at least 30 minutes of functional MRI data, but more is better. If you have less than 30 minutes, the reproducibility of your test-retest reproducibility of your metrics is going to go down quite a bit. Resting state has been tested in what I'm going to talk about, but other kinds of fMRI should work. And so hitting these temporal and spatial targets are going to require a multi-band EPI sequence. And I'll remind you, if you can, to save a single-band reference image. That's very helpful. One other sequence you want to get is some kind of a field map. We recommend 2-phase encoding reversed spin echo images. that match the fMRI data in terms of the geometry and the distortion. And that allows us to correct the images for B0 generated geometric distortion, for intensity and homogeneity from the receive field of the head coil, and we can even use this to estimate flip angle inhomogeneity, or B1+. So all of today's images are going to require, analyses will require only these images. So what do we want to do with pre-processing? We want to remove MRI-based image distortion so that all of the images represent the subject's physical space. We want to get images lined up across modalities and within modalities to get rid of the effects of motion. We want to make geometric models of the brain's major structures, things like cortical surface meshes and subcortical segmentations. And when we do this pre-processing, we want to avoid blurring the data. So not using interpolation methods like trilinear, but if possible, things like spline that are much sharper. And then we don't want to be overtly smoothing the data either. Also, we want to get areas aligned up across subjects. And so that raises the question of how should we format our data to be able to maximize cross-subject alignment. And so the HCP developed a new framework for analyzing fMRI data and other kinds of data. And we're going to consider the gray matter structures according to the geometrical model that is best suited to each of those. So that means surfaces for the sheet-like cerebral cortex and volumes for the globular subcortical nuclei. And so we sort of combine vertices and voxels into this term gray ordinates here. So we have 30,000 left hemisphere surface vertices, another 30,000 for the right hemisphere surface vertices, and then another 30,000 voxels across 10 subcortical structures here, giving us a total of around 90,000 gray ordinates. And we're going to register the individual's data on the surface using nonlinear surface registration, and in the volume using nonlinear volume-based registration. And gray ordinate-based analysis, or SIFTI analysis, actually allows us to greatly reduce the uncertainty in spatial localization that's typically found in traditional brain imaging studies. So how do we get areas lined up across brains? We can take area MT, the visual motion area in humans, as an example. So if we use a volume-based registration, we don't do very well. So we end up with only 46% overlap here. We actually have two separate hotspots on the surface here. If we move to a surface-based registration, we do substantially better. We get over 50% overlap, only a single hotspot. But you can see with these white arrows, we're actually having some areas that are still misaligned. And so if we go to an aerial surface-based registration, we can push that up to 100% overlap. And by aerial feature-based surface registration, what I mean by aerial features are things like architecture, function, connectivity, or topography. So the tools for neuroimaging HCP style protocols and MR sequences are available humanconnectome.org up here, and the CMRR website for the sequences. Software, the HCP's multimodal preprocessing pipelines, MSM-all pipeline are available on GitHub, as is the MSM algorithm itself. Connectome Workbench at humanconnectome.org. The fully preprocessed and aligned multimodal data of just under 1,100 subjects is available at humanconnectome.org. And then finally, there is still time until about maybe the end of this week, if you're interested more in these topics, to come to the HCP course in Portland, Oregon, which is in July. All right, so on to the HCP's multimodal cortical parcellation. So why parcellate the cortex? You've heard several speakers before me and have different opinions. Sort of my take on this is we want a map of the cortex to know where we are in the brain. If we're able to have this map, it can improve communication between investigators and comparison across studies. If we can agree on the borders of an area, it helps us to study that area's properties in detail and know what we're talking about, the same thing. And I like to go back to Marty Serino's 1995 science paper in the early days of fMRI to show that it was possible to do things in such a way that even today we can know exactly what cortical areas he was measuring. So he was able to map out V1, V2, V3, and V4 using early 90s fMRI data by processing on the surface. Parcellation also helps us to reduce the size and complexity of data while enhancing statistical sensitivity and power. You can think of it as a neuroanatomically informed method of smoothing, much better than unconstrained smoothing, and it helps avoid a lot of the methodological difficulties about taking data and sort of summarizing it down to single points in 3D space if you're interested in area level effects. So again, my opinion, what do we want in a cortical parcellation? Ideally, I would think it would have the following 4 qualities. It would be based on hundreds of precisely aligned subjects so that it does a good job of representing the typical aerial arrangement of the population. It ideally is going to reflect complementary and converging evidence from multiple modalities across the whole cerebral cortex, and reflect the existing terminology in the neuroanatomical literature. If an area has already been discovered, try and use the name that was used before, not come up with a new one. And then we want to be able to take that parcellation and apply it across subjects based on multimodal fingerprints in an automated way. And so this parcellation I'll tell you about has these 4 qualities. What do I mean by hundreds of well-aligned subjects? Well, we can take this group average myelin map here from 210 subjects. So the myelin, red is high myelin, and the blues and purples are lower myelin. And so despite this being a group average myelin map, we can see fine spatial details like this little notch in somatosensory cortex, right where that white arrow is pointing there. And in an independent group of 210 subjects, we get a very similar map. These fine details are present in both of them. And so this is not your typical blurry average, and Dan, who'll be talking later, has actually written a whole paper on these variations in myelin mapping. Task fMRI maps can show the same fine spatial details if you don't smooth them. Here we have the same group average maps for a story task, and we can see this little hotspot here. We'll talk more about this area 55B in later slides, but it's very highly reproducible. And these correlations, these group maps across these 2 independent groups of subjects are really, really high. They're quite close to 1 for myelin, task, and resting state, even though I don't show it. So how do I turn this data into a cortical parcellation? So most parcellations were made with only one of the modalities: architecture, function, connectivity, and topography, and the HCP measured all 4 of them. So we can use gradients as an objective measure of the locations of where these modalities are changing rapidly. These represent potential aerial boundaries. And gradients also can be used to provide a common measure that we can compare across modalities. So what makes a gradient convincing as an aerial boundary? Well, if we've got agreement in spatial location of a particular boundary in 2 or more independent modalities, that's really the strongest evidence to me that you have a real boundary there. Also, it's important to have statistically robust and significant evidence of multimodal differences across the boundary in more than one modality. If it's present in both hemispheres, that's kind of like an internal validation. We might not require that, but if it's present in about the same place, that gives us more confidence that it's real. Obviously, we don't want to be mapping out boundaries from imaging artifacts. And then if we think of things in a Bayesian way, if there's prior evidence of in the literature of a boundary, it's more likely to be real. So once we've sort of gotten our set of boundaries that we believe, the next question is, how many of these areas have actually been found in the prior literature? Which ones are new and which ones have been described before? So on to the specific modalities here. We'll focus on myelin first. So we're going to be particularly interested in where myelin content changes here. So now the maps, the red show where you have high myelin changes, greens, oranges, and yellows, somewhat less, all the way down into blues, and then the purples are less myelin change. And so the spatial gradient gives us an objective measure of where the myelin is changing, and the local maximum of this gradient is the most likely location of a potential aerial boundary. And some of these transitions are larger than others, but really what's going to matter is those transitions that agree across modalities. Cortical thickness can also be used in the same way. So here's a cortical thickness map, and I'm going to draw your attention here to the central sulcus, where we have a very distinct boundary here between motor cortex, which is on the anterior bank, and somatosensory on the posterior bank, and a really strong gradient here. I asked Saad if he's taken a look at his boundary in relation to this, and I'll be very interested to find out if it shows the same thing. I also want to draw your attention to the fact that we're focused here on the cortical thickness effects of an area. So gyri are thicker than sulci, and so we've sort of tried to correct for that by regressing out folding. We can do the same thing with task fMRI that we're doing with architecture. So here's a task fMRI contrast map. Positive areas are more active while listening to a task, and negative areas more active during rest. And we can take a gradient of a task fMRI map, just like an architectural map, but I'll point out that we're focused here on effect size maps. So beta maps or percent bold change, things like that, are more biologically interpretable than our statistical maps, which also depend on the data, how much data you have, what is the pattern of the noise, and things like that. And then finally, resting state functional MRI. So here we've got a seed location, this white dot, and the positive areas in the yellows and reds are functionally connected. And we can make a gradient of functional connectivity here to show where the connectivity pattern changes as you step across the surface and by how much. So here's a different functional connectivity pattern. Here's a different one. If I had a keyboard here, I'd go back and show it to you again, but I don't have a keyboard here. So if we focus on this middle pattern here and compare it to the task fMRI map, we can see that, as is often the case, areas that are functionally connected. I have a mouse wheel though, so I'll give that a try. There we go. That's actually much nicer. All right, so you can see that the areas that are functionally connected are also activated together in a task, and that's often the case. All right, so what about topography? I won't have enough time to discuss this in detail today, but Dan tells me he's going to talk quite a bit about this in his talk, so I'll let him cover most of this. I'll just point out that it's possible to map visuotopy with retinotopic tasks or resting state fMRI. In either case, topography allows us to map whole visual areas, where if we just did a simple clustering of, say, resting state connectivity, we wouldn't be able to map, say, V2 and V3 as being separate areas where we got the whole area. We would, say, get a cluster that was V2 and V3 peripheral and another cluster that was V2 and V3 foveal. If we actually use the topographic mapping, we can do this in resting state or task and get the whole cortical area. And there are also somatotopic subareas in sensory motor cortex. So let's put it all together for one cortical area. We'll focus on this lightly myelinated strip here. 55B, it's right in front of the motor cortex, and there are two eye fields on either side of it. And so these white dots here are along the gradients, the most likely areal boundaries. It turns out this area has unique activity during the story task relative to its neighbors. And so the task gradients line up with the myelin gradients. If you put a seed here in the perisylvian region, we can see we've got selective connectivity to that area, not its neighbors. But if we put a different seed here up in the interparietal sulcus, where this myelin hotspot is, we've got connectivity to the two eye fields, but not to 55B. And so, as you saw already in the previous slide, we've got strong gradients around this area. So multiple independent modalities, architecture, function, and connectivity are all agreeing on an area. And the last step is to see, did anybody else find this area in the literature? It turns out, back in the 50s, Adolf Hopf was doing a lot with myelin mapping invasively, and he made actually the first real myelin maps on surface drawings in this case. And so we can see here's the motor cortex, the two eye fields on either side, and there's 55B. So the overall methods of how do we go about this, we made the multimodal parcellation from one group of 210 subjects, the 210P group. We defined the borders based on group average, architecture, function, connectivity, and topography. And we used a semi-automated parcellation approach. One of the reasons we did that is because it's my belief, and David's as well, that neuroanatomists still have a role to play in figuring out what is the information that's real versus artifactual, and also in where is the most likely location of a boundary. So we picked the information that seemed most useful, and we drew an initial boundary, and then we let an algorithm optimize that boundary so that it best followed the multimodal data. So the final boundaries are drawn by the algorithm, but it's informed by the neuroanatomist. And finally, areas were identified with reference to the prior neuroanatomical literature, trying to keep area names the same when possible. So we had a few predictions going into this exercise. Based on partial human and monkey parcellations, we thought there'd be somewhere between 150 and 200 cortical areas per hemisphere. We thought there'd be wide variability in areal size and shape across the cortex, and examples of inter-area heterogeneity, such as the sensory motor topographies. So we found 180 areas per hemisphere. 97 areas were new, hadn't been described before, or were subparcellations of existing areas. And 83 areas had been described before per hemisphere. And you can see there's wide variability in the areal size and shape across the cortex. We've got long, thin areas in sensory motor cortex. We've got sort of horseshoe-shaped areas around the visual areas, and pretty much everything in between here. Including, we were able to accurately parcellate many well understood but previously troublesome areas for more automated approaches, such as the sensory motor cortex and the visual cortex. And then some areas contain the topographic subareas. So I wanted to give the parcellation kind of an intuitive color scheme, focusing on the three main input streams to the brain: auditory, sensory motor, and visual, in red, green, and blue. And then the two strongest anti-correlated cognitive networks: task negative or default mode in the darker colors, and task positive or anti-default mode in the brighter colors. And if we look at this map, we can see some cortical areas are sort of core areas, and others are kind of in between. So if we take this, this was the hot spot of myelin in the interparietal sulcus here, LIPV. We can see it's kind of in between visual and somatosensory motor, and that makes a lot of sense because this area has strong inputs from these locations in, say, monkeys. So validation, are these aerial features really different in an independent data set that wasn't used for parcellation? We're going to divide the features into 4 categories: thickness, myelin, task activation, and resting state connectivity. And we'll look for robust and statistically significant effects across each aerial border pair, and our degrees of freedom for the statistics will be across subjects. We'll use really stringent thresholds here. We'll use a Cohen's d of 1, which is a really big effect size, and then a very stringent p-value corrected for multiple comparisons. So the red borders are those that matched all 4 categories, and that's about a quarter of the boundaries. The orange matched about half, or 3 categories. Green is 2 categories, another quarter. And it was really a small number of boundaries that matched only 1 category, or none, although it turns out that the 40 that didn't make at least 2 categories, and the 2 that didn't make any, were always statistically significant. It was this Cohen's d threshold that they fell below. So you can use this way of visualizing the information to see which modalities were useful for distinguishing each border. Cortical thickness was the least useful, but still useful. Myelin was next most. Task was next. And resting state was the most useful. So you can do parcellated analyses with these data. So we've got about 60,000 data points here on this map, myelin map, with the boundaries overlaid. But if we average the myelin content within each area, reduce it down to only 360 data points, we can see that there's not much change in the overall pattern, showing that we have a nice parcellation. We can also do functional connectivity analyses, say mapping out the default mode network with either full correlation or partial correlation. A much sparser map here, but we still see a nice default mode network. We can do a parcellated task analysis. This is a working memory task. These are all tasks by areas along this axis, or the story task, which we see down here. Now, if we compare doing the parcellation first and then fitting the GLM, which is what we did down here, versus doing the fitting the GLM first and then doing the parcellation. If those things were equal, these blue dots would be right along this red line here, but actually the line is steeper, and that indicates that you actually gain signal to noise by parcellating first and analyzing, fitting to a GLM second. So to summarize this section, 180 cortical areas within each hemisphere, and that was within our expected range, 97 new, 83 existing. And these vary widely in size and shape, and some have topographic heterogeneity. Parcellated analyses can be performed with most modalities: architecture, function, or connectivity. Minimal loss of detail with a good parcellation. If you're interested, the parcellation is available. Also, here is a new database for sharing HB-style published results. And what I would recommend if you're going to use Connectome Workbench to generate your figures is you can actually make and annotate multi-panel figures inside of Connectome Workbench. You can then save the state of Connectome Workbench or save it as you're working. as a scene. You can export an image for your paper, and if you've done all this, it's super simple to just upload your scene and your data to Balsa. The website and Workbench will take care of everything for you, and your data will all be shared. Exactly all the data that was needed to reproduce the figure will be shared publicly. All right, on to individual subjects, the last topic. So I want to focus on atypical cortical areas here. We'll use 55B as our example again, and I'm going to show you a shift of 55B. So first, the typical relationship between 55B and this sort of comma-shaped upper limb sensory motor region. So normally 55B points at the comma's tail, but in some subjects it actually is shifted up and points at the head of the comma here. So an aerial feature-based surface registration will preferentially align this large feature here relative to this small one, causing this shift. So what does this look like in real data? So we've got a resting state language network here, language task. We've got the upper limb sensory motor region and a myelin map here. This outline is the group location of 55B, so we can see it's connected in the language task, or in the language network. It's active in the task, slightly myelinated, and it sort of points down to the tail. So a typical subject looks a little noisier, but still it's a very similar pattern, has all of those features. But in this shifted subject, you can see that the functional connectivity, the task activity are now sort of pointing up to this white dot. There's high myelin here in the group location, and so this is example of the shifted pattern. Here's another example of the shifted pattern. Same thing, we're sort of pointing up towards this white dot here. What about a different topology, where 55B splits in half and the two I fields, FVF and PF, join together? So here's our typical arrangement. We've got motor cortex back here, the two I fields, and 55B. Some subjects, though, have this pattern where 55B has split into two pieces and the I fields come together and fuse. What does that look like in real data? So these three panels are going to be the same. We've added on motor cortex and the two I fields in terms of the group outlines. And we've also subbed out here the dorsal stream visual network, which is connected to the I fields on the bottom panel. So here's another individual subject that's typical. We can see that connectivity to the dorsal stream, which is absent in 55B, and these same panels look very similar. If we look at a split subject, though, here we have two hotspots of functional activity, or functional connectivity and functional activity here, these two pieces at 55B, and between them you have an absence of this. In that location of absence, we have high myelin, we have connectivity to the visual stream network, dorsal visual stream. So see how these things change together. And here's another split subject. Again, we've got the two foci of connectivity and activity, the high myelin that sort of runs right between them and the dorsal stream connectivity. So how are we going to solve this problem automatically in individual subjects? Turns out 89% have the typical topology, but that means 11% have another topology. We want our canonical parcellation to be based on the typical topology, but we want to be able to account for these atypical individuals as well. And it turns out aerial feature-based registration, while it can change the size of an area or move it around, translate it in space, it can't actually swap areas or deal with these splits and joins. So we'll use a multi-layer perceptron to solve this problem. We'll use multimodal features to learn each area's aerial fingerprint. We'll make a few reasonable assumptions, like V1 is not outside of the occipital lobe. We'll simplify the problem using an area class and its surround and a good distance away from the boundary where the area is likely to be. We'll combine across aerial classifiers to find the 180 aerial classifiers to find the highest aerial probability. And so what does this look like at the individual subject level? So some HCP subjects were scanned and analyzed through the whole pipeline twice. So here's an example subject. We've got folding, myelin, language network connectivity, and here's the output of the aerial classifier. Again, the outline is the group 55B, and we can see very nicely this here is the final output of the classifier, and that's the probabilistic output. Very nicely finds 55B in the expected location. If we do it all again, it finds the same thing. But this is the easy question. Registration would have gotten these lined up already, as you can see. But here's a split subject here. We can see there's a split in the language activity and the myelin, and we can see that split shows up in the classifier outputs. Here's a shifted example. Again, we can see the shift in the raw data, in the probability output, and in the final output. So the aerial classifier is able to reproducibly identify Area 55B, and also these atypical topologies are stable in time. They're, a real feature of those particular subjects and not ephemeral. So how good is the aerial classifier across all of the subjects? Well, the classifier is trained on this data here. It never gets to see this validation data here. So we can see it does close to 1 actually on both data sets. Turns out that on our validation data set, out of all areas and all subjects, 96.6% of areas were detected. If we leave out the task fMRI data, we do almost as well. And so that means that this aerial classifier will work for studies without the HCP's specialized task fMRI battery. We only need T1, T2, a field map, and fMRI to use it, as I said at the beginning. So what about reproducing the multimodal parcellation using only aerial fingerprints? So we can apply the aerial classifier to individual subjects, generate individual subject parcellations, and then average each area's map across subjects to make probabilistic maps of the areas. We've got V1, M1. Here's 55B and 46 are a little bit more variable, but these probabilistic maps are very similar across the two groups. What about reproducing the overall parcellation? We can use maximum probability maps to do that, and that's what we see here. So the aerial boundary gray ordinates are displayed. Blue means it's a boundary in 210p, red for 210v, and purple for both. And you can see there's very high overlap, a very good agreement. Correlation of these parcellations is near 1, which is in line with those original data that was used to generate the original parcellation. So to summarize, individual subjects contain atypical layouts of cortical areas that cannot be aligned with aerial feature-based registration. The aerial classifier can find those atypical areas automatically in individuals. We can replicate the group parcellation, and the aerial classifier and individual subject parcellations are coming soon. I can take any questions.